Welcome to the first video of our third class session preparation set of videos. I wanted to go ahead and start this video reviewing how we assign formal charge, and then we'll move on into reviewing Lewis structures and eventually get to resonance forms. So, review, how do we assign formal charge for an atom? And the answer is we count the total number of things around an atom. Each single bond counts as one thing. Each electron counts as one thing. So let's take carbon as an example. Here we have the methyl radical, and there is no formal charge assigned to the carbon in the methyl radical. It is neutral. It has 3 single bonds and 1 electron for a total of 4 things. We know that carbon has 4 valence electrons in the neutral state. Hence, in this example, the carbon has no formal charge. Here we have a carbanion, the methyl carbanion to be exact. We have 3 single bonds and 2 electrons for a total of 5 things. And if we remember that carbon has a valence of 4 electrons in the neutral state, well, 5 things is one more thing. So we need to place a formal negative charge on the carbon atom. And here we have the methyl carbocation, which has 3 single bonds and no electrons for a total of 3 things. And since 3 is one fewer than 4, we need to add a formal positive charge to the carbon atom. So organic chemistry is primarily concerned with hydrogen, carbon, nitrogen, and oxygen. We might throw in a few halogen atoms now and then. But these are some of the primary atoms that we encounter in organic molecules. So it's good to know off the top of your head what the neutral valence state is for these atoms. For hydrogen, the neutral valence state is 1 electron. Carbon, 4 electrons. Nitrogen, 5 electrons. Oxygen, 6 electrons. And any halogen is going to be 7 electrons. So let's look at more examples. Here we have hydroxide, the hydroxide anion. There are 7 total things on oxygen. Well, we just said that oxygen has a neutral valence state of 6 electrons. 7 is 1 more than 6, so we have to add a formal negative. Here we have the H3O plus cation, the hydronium. So we have 5 total things. That is 3 bonds plus 2 electrons, 5 total things. That's 1 fewer than 6. So we need to add a formal positive assigned to that oxygen. Now, interestingly, like I said, don't get confused by the octet rule. For the hydroxide anion, the oxygen is sharing and or possesses a total of 8 electrons. Its octet is satisfied, and yet the oxygen gets a formal negative. On the hydronium cation, our oxygen has a formal positive, and yet it is sharing and possesses a total of 8 electrons. Its octet is satisfied. So just following the octet rule isn't going to help clue you in how to assign formal charges. You've got to use the method that we just reviewed. So, moving forward. Recall the concept of resonance. You can push lone pairs of electrons and or double bonds to move or create charges on atoms within a molecule. So let's consider the formamide anion. Here we have a formal negative charge on our nitrogen atom because it has a total of 6 things, 4 electrons and 2 bonds, and so that's 1 more than the 5 electrons in the neutral valence state for nitrogen, so we add a formal negative assigned to that nitrogen atom. Now we can, through a rational arrow pushing, mechanism, write another resonance form for this formamide anion. We can take a lone pair of electrons on nitrogen and use them to form a double bond between the nitrogen and the carbon. Well, carbon already has 4 bonds, so if we use that pair of electrons to form a double bond between the nitrogen and the carbon atom, we have to break one of the bonds that carbon has to oxygen in this case, because we don't want to separate the atoms. I've seen students try to break hydrogen off, but then we're not drawing a resonance form, we're drawing a different molecule. So if we do this arrow, then we have to break one of the 2 bonds in this carbon-oxygen double bond, and we'll symbolize that by an arrow that's double-headed because we're moving 2 electrons, the 2 electrons in that bond up onto oxygen. And so if we do that, now our nitrogen atom has a total of 5 things, 3 bonds and 2 electrons. So it's in a neutral valence state, so it has no formal charge associated with it. However, if we look at oxygen, it has a total of 7 things, 6 electrons and 1 bond. So that's 1 more than its neutral valence state of 6, so we have to add a formal negative charge. Again, there's this idea of a resonance hybrid, that electron density is sort of delocalized over those 3 atoms. The reality is a little more complex, and we'll touch on that soon. But one can think that the formamide anion is neither described perfectly by either resonance form, and one way we symbolize this might be drawing out some sort of structure in which we've delocalized this formal negative charge. We might consider a partial negative charge delta A minus on oxygen and a partial negative charge delta B minus on nitrogen, and those partial charges would add up to 1 full negative charge. So what can we say based on our knowledge of relative electronegativities about the conditions that we might expect for the fractional or partial negative charges, delta A minus and delta B minus, that describe the resonance hybrid best? Would we say that delta A minus would be equivalent to delta B minus? Would delta A minus be less than delta B minus? Well, the answer in our notes suggests that delta B minus as a fractional charge is going to be less in magnitude than delta A minus as a fractional charge. Why is that? Because oxygen is more electronegative than nitrogen. It pulls harder on the electrons, and so we would expect it to have a greater fractional minus charge associated with it. This gets to the idea of major and minor resonance contributors, and we'll pick that up in the next video.